Hello Year 7. We're going to look at sound waves today and how we describe them in a little bit more detail. Hopefully last lesson you learned that sound waves work by vibrations passing from one particle to another. So the particles have to bump into each other in order to pass the sound wave along. That's why if you did something like hold your finger to your voice box, you should be able to feel it vibrating. If you did the fork experiment where you hit the fork and put it in the water, you'd see that transfer of energy from the fork into the water. And that's where phrases like this one comes from. In space, no one can hear you scream. Why is this true? Because in space we have a vacuum. Now, a vacuum is an area where there are no particles at all. So if there are no particles, then sound cannot travel because there is nothing to pass on the vibrations from one form to another. So my first task for you today is to look at this set of sentences here. I want you to copy this down and think about the words that go into each of the blank spaces. So take a chance now to pause this video and fill in the blank spaces. Okay, so you've had time now to fill in those blank spaces, so let's go through what the words should be in each gap. Sound is produced when an object vibrates. In instruments like guitars, it is the strings that vibrate, whilst in wind instruments, it is of course a column of air that vibrates. The vibration of a drum skin makes sound. Vibrations are often so small and fast that they are invisible. The vibrations transfer energy to air particles. The energy is passed on in waves. When a loud sound is made, more energy is transferred by the sound wave. The amplitude of the wave is larger. Now, we haven't really looked at this term amplitude. It's one of the new words that we're going to look at today. So it's just a reminder then that those particles are causing vibrations. But what we can see here is this is where the particles are colliding with each other. And that vibration gets passed on through the air particles until it reaches your ear at the other side. Now that's called a longitudinal wave, where you've got the direction of the wave and the energy flowing in the same direction. But we use this other type of wave to show what it is that we are seeing. Okay, so this is the wave diagram that we use, and you can see how it corresponds to those different waves that we have there. So, let's have a look at some key words. We're going to look at the words wavelength, amplitude, and something else that's not on this diagram is frequency. So, what we always have whenever we do these sorts of diagrams is we always have our baseline along here. So the wave is always measured by how much it moves away from that baseline. And this area from this baseline up to the top here is known as the amplitude, or the height of the wave. And it'll be the same both above and below the line, so we can measure either of those. The wavelength is the distance from two of the same points. Okay, so either from here to here, or we could measure it from any other point. So from here to here, this would also be one wavelength. Similarly, we could go from this point here to this point here. As long as you're going from an area where the line has gone both above and below completely in one complete cycle. Okay, so you can see how it says here, one complete cycle. So that is a wavelength. You need to be familiar with what these words mean and how to measure them on these diagrams and how to show a different sort of wavelength as well. So now we're going to have a look at the definitions for these different words. And you'll need to write these down somewhere where you're going to look at them and remember them. So the wavelength, as we said before, is the distance between a point on one wave and the same point on the next wave. The frequency, which we haven't looked at yet, relates back to wavelength. It's the number of waves that are produced by a source each second. Now, usually when we're in the classroom, I would explain this as, imagine that one bus is one wave, or one car is one wave, and you're standing at a road and you're measuring how many cars or how many buses go past each second. That would be your frequency. So on a slow road, that frequency would be quite small. You'd only have one wave or one car going past every second. On a motorway, that might be a few more, although hopefully they're not going that fast. But you get the idea. So if there are more waves going past each second, then the frequency is higher. This generally means that you can follow a pattern here. So if a wavelength is longer, then the frequency will be lower. If a wavelength is shorter, then a frequency will be higher. But we'll come back to that in a second. So there's an important calculation that you need to be able to do, and that is this one here. Okay, so frequency is measured in hertz, but we can measure the frequency by doing a calculation. It's simply just the number 1 divided by the wavelength, and that will give you your frequency. And as I said before, longer wavelengths will give you longer frequency is kind of the from phrase, but higher frequency. Shorter wavelength will give you a shorter frequency. Now remember, if at any point you find that I'm going too fast for you, you can pause the video, make your notes, and then resume. So the amplitude of the wave is its maximum disturbance from its undisturbed position. So I'm going to take you back to this diagram. Remember, it's that height. So this is the undisturbed position, and this is the height of it here. Okay, so it's going from that baseline bit to the top. And lastly is this word pitch, which you're probably familiar with from your music lessons. This is how high or how low a tone is. So talking in a really squeaky voice like this is a really high pitch, and talking in a really low voice like this is a low pitch. And we can relate that back to our frequencies, which we'll do shortly with a little experiment. So let's just look at some comparisons of waves. So the first diagram that I have got here is a low amplitude, and the second diagram here is a high amplitude. Notice that on both of these diagrams, the wavelength is exactly the same. So if we go from the start or the same point on two waves, so let's go from better colour, from here to here, and then we do the same over here, from here to here, you can see that that distance is the same. We've got 5 boxes on both sides, here and here. Excuse my wonky lines, you get the idea. So the wavelength hasn't changed, so we haven't changed the actual pitch. It hasn't got any higher or any lower. What has changed in this instance is the height of the wave. So if we look at that baseline part that goes through the middle, which is probably about here on this diagram. Okay, let's try and get that a little bit more in the middle. A bit tricky on this one, but you can see on this one, the height of the wave is much higher, and this one, the height of the wave is much smaller. So therefore, this is the one that is going to therefore be much louder. And this one will be quiet. On the right hand side, the loudness of these waves is the same because they haven't got any higher or any lower than each other. Okay, so the height of the wave is pretty much the same, almost. But what has happened here is the wavelength has changed. So if we look from the same point to the same point, this one is quite long, whereas this one here from the same point to the same point, it's quite short. So this one is the higher frequency, and therefore it will have a higher pitch, and this one has a low frequency, so it will have a lower pitch. Now sometimes sounds also sound different. They can be in the same pitch and they can be the same loudness. So for example, a piano and a violin might play the same note, but they don't sound exactly the same. And that's because the actual wave itself will change its shape, so it can still have the same actual wavelength. And it can have the same height, the same loudness. But the actual sound is different. So let's look a little bit more at these sounds. Time for you to do a little bit of an experiment, and hopefully it's not going to annoy the people that are around you too much, so don't do this for too long. But take yourself a ruler, try not to use a bendy one or one that bends in half in the middle because you might break it, and you're going to put it on the edge of the desk, and all you're going to do is twang your ruler. And I want you to just think about, how do you change the sound? So how do you make it lower pitch? And how do you make it higher pitch? I want you to think about, what are you actually doing to the length of the ruler that's hanging off the end? So is the lower pitch when you've got more of the ruler or less of the ruler? Similarly with the higher pitch. And also think about, how do you make it louder? What do you have to do to the ruler in order to make that sound much louder? And then think about how that links back to your wavelength and your amplitude. I'll give you a chance to do this now, so pause the video. Okay, so hopefully you've had a chance to experiment and you have found out that when your ruler is quite long, so you've got on the edge of your desk your whole bit of ruler hanging off the end there, your sound is quite low. And what you might have also noticed was that the rate at which it vibrates backwards and forwards is quite slow enough that you can actually see it vibrating backwards and forwards each time. What you hopefully then found when you used a shorter bit of the ruler, so on the edge of the desk, not much of your ruler was on the end, your sound was quite high, and it may have vibrated so quickly that you didn't actually see the vibrations, and that's because your frequency was much higher this time. So your wavelength was shorter and your sound was higher. So that's a summary of everything you need to know about these keywords and how they relate to the waves. You've got a worksheet now to be getting on with. If you get stuck at any point, you can research on websites such as BBC Bitesize, you can watch this video again, or of course you can email me for help and support. I hope you find this useful, and I'll speak to you all soon.